Welcome, welcome, welcome to Perry Marshall's Q&A session. I am Tana Marshall. I'm going to be moderating today's discussion with Perry. I'm basically just here to make sure that everything runs smoothly, that no one is talking over each other, that everyone gets their questions answered. So we're going to start with a quick question. If everyone goes to the bottom of their screen and presses participants, do you see a button that says raise hand?
No.
No? Okay. If you go to the bottom of your screen, do you see a button that says reactions?
Yes.
Okay, so here's how we're gonna do this today. I wanna make sure, oh look, someone actually raised their hand. So some people have that. If you have the raise hand button, feel free to use that if you have a question. If you don't, I'm gonna ask that you use the reactions button. Use whatever reaction you would like. I am here to notice if someone gives a reaction. And I'm gonna ask that you do that just to let me know you have a question. I'm gonna put your name on a list just to make sure that everyone gets their questions answered in an orderly fashion. That is what I'm here for. So if we want to practice, if anyone has a question that you want to start with, I guess we could do that. Or Perry, if you'd like to.
Before we get into questions, I'd like to just highlight a couple of things. First of all, I just want to thank y'all, you guys. I really enjoyed doing this conference and having you guys a part of it. And there was lots of action, and like the chat box was always popping. I want to just mention a few things from my presentation. You know, everybody had to do really fast presentations, so I just want to mention a few things. At the very end, I put this on the screen. I said, cancer is not an algorithm. Cancer is a disease of identity and volition. And a few years ago, it kind of crystallized for me that matter and energy and information and cognition are three very distinctly different things. And for the most part in science, they've been mixed together. And because of that, I think we have a lot of confusion about cause and effect. And you know, Einstein said you cannot solve a problem at the same level of thinking that created it. And I think that applies to cancer. So there are three ways at which you can attack cancer. You can attack cancer at a chemical level. You can attack cancer at a code level. And you can attack it at a cognition level. So the chemical level is chemotherapy and similar things like that. The code level would be attacking it as a genetics problem, which is more sophisticated and potentially much more effective. But because of what I do for a living, I have watched people try to attack cognition problems at a code level, and your spam filter does that. And spam filters, well, if you go study spam filters, the ones that work, they mostly work based on who the sender is, not what the sender is saying, right? Like we all know that you can jack up a spam filter just by misspelling a bunch of words. There's an infinite number of ways to misspell something. And so if you go back 10 or 15 years, you have some very ineffective ways of thwarting the spammers. A much better way is to figure out, well, if like Google knows who that sender is, they'll like, oh, that person's a spammer. And I think we have to deal with cancer at that level. I think there are technological parallels to all of this stuff. So that's my opening salvo. And I am delighted to just do open Q&A with everybody here. So Tana, who's maybe you could pick the, well, however you want to do it, Tana. Yeah.
Yes. So first of all, does anyone have a question they'd like to start us out with? You can put a reaction or just announce yourself. Any questions? Any questions are welcome.
Well, I will be happy to just riff until you know, somebody let me share my screen again. Well, so
Sorry, I just saw Carlos. I saw you just come off of mute. Did you have a question?
Not yet, no.
Okay, perfect. Go ahead and riff.
I just arrived, so I don't know exactly what has been discussed.
Yeah, for anyone who has just come on, this is a Q&A session, but if anyone doesn't have a question, Perry's just going to go ahead and continue talking about everything that you have heard him talking about up to this point. He'll continue elaborating. So chat me, send a reaction, anything like that if you have a question, and I will let Perry know. Otherwise, take it away.
yes, so the normal dogma in biology is that evolution is blind.
Hey, we actually have a question from Doru.
Yeah.
Doru, go ahead. Oh, I can't hear you.
So
there we go. Okay.
So Perry, I'm a cancer doctor, and I've been, treating more than 10,000 patients with cancer. So the first question I think is, how do you define cancer? Because I think that you cannot really treat what you don't understand. So the first question you should start with is, what is cancer? Because you said cancer is or is not, but how do you define cancer in order to discuss about it?
That's a great question.
I think there might be other places right now that maybe
you might need to mute somebody, Tana.
I would never count this out, and I wouldn't short it to where it's sitting right now. It just probably doesn't have my attention at the moment. But
you can, Tana, there's a mute all here.
That's realistic.
I'm gonna mute everybody, and then we can unmute people as necessary. Okay, so my definition of cancer is cells evolving out of control, and it is when a cell starts acting like a unicellular organism in some random environment rather than a multicellular organism doing what it's supposed to do. So, skin cells are little soldiers, and they're supposed to march, and they're supposed to act like skin cells, and liver cells are supposed to march and act like liver cells. And so my understanding of the real problem in cancer is when cells start doing transposition rearrangements. They start possibly exchanging genetic data with other cells. They start doing chromosome rearrangements, like Henry Hing likes to talk about. In fact, I'd welcome Henry to tune in on this conversation. And the cell starts acting on its own accord rather than as a part of the community that it's in. So Doru, is that anywhere close to an adequate explanation in your estimation?
The thing is that according to whom you talk, you'll get different definitions.
Yes.
Talking to Dr. Weinberg, he's going to tell you that you have these hallmarks that he described of cancer. If you talk to Dr. Sonnenschein, I think he's going to tell you something different. If you talk to Dr. Lee, he's going to tell you that basically you have this polyploid cell that looks like an egg that is going to start the development of cancer.
Yeah.
Dr. Heng is going to tell you that basically it's chaos that is happening at the level of the cell. So that's why I think it's important when you're starting this this discussion to define to what paradigm you apply to in order to to be in that paradigm and further down the road get everything very clear.
You know what it's like? It's like defining life. You ask 100 scientists to define what life is, and you get 100 different answers. And one of the reasons is it's almost ineffable, right? Like, I mean, that's a philosophical term for almost out of reach, right? And so it's like some people say, well, life is self-replicating, metabolizing, balls of lipids, right? Or somebody says that, you know, life is anything capable of Darwinian evolution, which I don't think is a very good answer because Darwinian evolution is poorly defined, right? And so, so Doru, what is the simplest definition that you would give it?
I would say it's a modified cellular program.
Okay, I'd say that's pretty compatible with mine.
Right.
May I?
Yes. Hi, Carlos. Where are you from?
I am originally from Argentina, but I am now in Boston for the last 55 years, 60, sorry, almost.
Nice to meet you.
Well, there is a historical record. And the historical record has told us that cancer was a cell-based disease. And this idea is just a century old. And we have now very good evidence that indicates that the basis of that consideration has been falsified. As people in the last week's deliberations verified, mutations that used to be the central issue have been the central issue that define the cancer cell has now been showing up in normal cells. So according to what theoreticians of science say, you have a theory, you falsify it, and you drop it. The problem is that in cancer, nobody is ready to drop it because dropping a theory of cancer is very traumatic. A lot of people live from cancer, as you know, and there is this popular thing that there are more people living from cancer than dying from it. So if you tell people that to drop the somatic mutation theory, they are going to sell their mothers not to do it. And they are going to find one thing and another thing, so they don't drop it, because unless they are funded, and this is something that was not discussed last week, money has a very important role in what cancer is.
Yes, it does.
And people have been selling us a bill of goods that turn out to be untrue, which is that cancer is a cell-based disease. And unfortunately, because of the vagaries of life in science everywhere, not only in the United States, but everywhere, unless you have a grant that will give, let's say, indirect cost to the university that you are working for, you are out. Now, unfortunately, I haven't had a chance to hear Dr. Reza, even though I heard her talk in a podcast, and I was quite impressed. She understands that there is a problem, and most people know that there is a problem. The issue is that the solution of that problem is very traumatic, and unless people eventually will drop their, let's say, ideas about how to survive in science, cancer will not be solved.
So, Carlos, I was at a funeral yesterday. I had a friend named Laura Middleton. She died April 10, but we couldn't figure out how to do a funeral until yesterday. So we went and had her memorial service. It was very beautiful. And there were a couple of people at the funeral who are my friends who had attended this symposium. And so we were all talking about it. And one of the things that I said was, I said, you know, I think one of the reasons that stage 4 cancer patients will get into treatments that have very little chance of working and will make them miserable, right? Even more miserable than they would have been otherwise, is they're so afraid of dying that that the terror just drives them to do desperate things. Well, I believe that the same is true of researchers, that if I drop the somatic, like fill in the blank theory, okay, if I drop somatic mutation theory, if I drop whatever, my career as I know it is going to be over, and
Right.
a different kind of fear of death. And what I have seen about all the scientists that I really admire is that most of them have paid a heavy price for the positions that they have taken. You know, I don't know if you were on the call when I told about a conversation I had with Jim and Joan Shapiro a few years ago. I was at their house and I said, we're talking about all the resistance to new ideas and stuff. And I said, well, Jim, that's what you get for being 25 years ahead of your time. And Joan looks up from the kitchen and goes, 30. And Jim has paid a price for the positions that he's had. You know, natural genetic engineering was not a popular idea for a really long time, right? Or let's see, we had, I want to make sure the other, Jinsung Liu was talking about how, you know, it took him like 5 or 10 years for people to figure that a pathologist actually knows what he's talking about, to publish something in a journal that's not about pathology. Jinsung, do you want to weigh in on that?
All right, so thank you. All right, Carlos, we finally meet. Huh? We, you know, tried to discuss the, you know, cancer origins a long time ago, but somehow we get, you know, disconnected. And I try, he said he always wants debate with a pathologist and about what is cancer. I say, here I am. I'll be very happy to, whatever you call it, debate or discuss, whatever we call it. So, you know, this is a really fascinating conference, and you know, with many people who have different ideas and you know, from different aspects to see what is cancer. So, I mean, this is fascinating. As Carlos said, all right, the scientists they have to come from a specialized you know, perspective, right? When you come to science, get trained, specialized in very disciplined. I'm amazed, you know, many those scientists actually do not have a pathology training, which is fine. All right, you know, if you study metabolism, you know, or cell biology, very specialized aspect, and then this is, you know, all good. You know, there's no problem. You know, you publish a few papers as long as you have people in your field, in your small group recognize your review grant, you got a career promoted, and then that's not the problem. However, you know, over, you know, course of my career, and then first actually, you know, I came to United States for 36 years ago as a student. Actually, at the year when Barbara McClintock received her Nobel Prize, I had no clue what kind of, you know, things talking about. You know, we were signed to read her papers. I had no clue. You know, largely failed that course almost because we don't know the jumping gene, we don't know genetics. I came from medical school, and then so I really had a, you know, hard time to understand this. But I did get the good trainings. All right, so over, you know, those years, and then I finished my, you know, PhDs in biochemistry, and then I did the postdoc in retrovirus HIV, and then I finished my pathology resident. And then when I doing pathology resident, I just realized how ignorant I am about the real cancer. I had a really hard time to look at all those cancers, you know, daily basis, because this is life-threatening. You know, you have to make a decision. You got the on the spot, right? Because the patients lie down over there. You know, you have to make a decision. What is cancer? What is not? So when I become a pathologist hired by MD Anderson, and then when you start the career, you have to start doing molecular biology, right? Otherwise, you will not go anywhere, right, in terms of career. So actually, the first 10 years I did all those transformation with Weinberg, okay? And, use his genes, get his constructs, which is great, those genes virus can transform those cells. I get my professorship, get R1s, get a tenure. But at the same time, over past, after the first 10 years, I just realized that whatever I do in the lab does not fit what I see. I have a very, very advantage. I said, I got a paid job. And I look at those cancers every day, which not many scientists have. I consider myself is lucky because, anything what I see over here, you can look at my, slides over, my office, just tons of those slides over there every day. Pretty much I've buried in a real cancer at the MD Anderson. So with all those different phenotype, all those tissues, teratomas, malignant mixed malarian tumors, germ cell tumors, I just realized that, I'm the one who actually looked at all those cancers. Really, we don't have anything that can explain what I see on the microscope. Because bottom line, for any people who wants to propose a theory, as I said, you have to explain, tell the patient, tell the doctor, is this benign, is this malignant, period, all right? So any other theory, if you cannot explain this, I know it's not good because, nobody will care if a theory, you say, all right, proliferation, somatic, a nucleoid. If you cannot tell a tumor in a benign, a malignant, that's no good because nobody wants it because clinically, you can debate among the different scientists or small group you have, but when you come to clinic, when you come to pathology, everybody do not know what you're talking about because that's not that we really care. So you must have something that integrated everything that you can see on the microscope, guide the patient's care. Then those things, have to be tested in the experiments, and then in the clinic, and then see you can integrate the different types of tumors. So it really will take anyone who really at the 10 years training to understand those different types of tumors. Otherwise, you're going to just look at very specialized aspects. I mean, everybody has his merit in any series. Mutation, actually, like what you said, Carlos, is not a mutation, but actually this is not entirely true. They do have some merit, all right? Some mutation do.
Which is the merit? Which is the merit? Tell me a single gene that when mutated produces a tumor, please.
No, this is not the question.
That is the question.
No,
because that is the question.
No, the question is
that is the question.
No, this is a question. Some you can sensitize the cell to tumorigenic process. For example, BRCA1, BRCA2, you're going to move your age 10 years younger. Okay, so let me finish it. I'm not arguing with you. Any mutation so far, no mutation has proved to be cause a tumor. And then there are plenty of yeah, that's right. But you will not say it is totally useless and then no rule at all. This is
Tell me what it is used for.
I mean, anybody.
I can tell you what it's useful for because I'm an oncologist, okay? You can use mutations to target them. And in lung cancer, for example, you're using the EGFR mutation to target them. And I've seen patients living for 10 years after getting an EGFR inhibitor. So you cannot, discard and say they're not useful. You can say, of course, that they're not at the origin of cancer, but it's a different story. But you cannot say they're not useful. I mean,
sorry, I
didn't.
Sorry, I missed it. What are these mutations good for? I missed that.
You can target them.
Tell me which is the target that you would do to a mutation that is a favorite of yours.
For example, the EGFR mutation in lung cancer. You have BRAF mutations in melanomas. I have a patient with anaplastic.
That is, if I may say, this is a correlation, right? It's not a causation, right?
No, wait a second. You said they are not useful. And they're useful because you can have drugs against them. I'm not talking about the origin here. I'm talking about what they're useful. Anyway, I think these are mute points. I think we should go back to the main discussion, and if
Yeah,
you find, yeah.
I don't want to get into a philosophical discussion about somatic mutation theory, because I don't really think that's the root issue of cancer anyway. I agree with Doru that you can find certain correlations, and sometimes you can have some therapeutic success.
Yeah.
Does anybody have a question about?
Yes, I have a question. I have a question.
Yeah.
So my question is, but before I ask your subject about the, and I just try to just use a very briefly, just answer one question of the previous discussed. So now we actually thinking the two phases of evolution. So initially, the macroevolution follows that actually gene mutation always stochastically help the cell population to grow. So it's not really, as such a initial. So we can discuss this more, Carlos, to say. But to answer the initially Dora's question, so you are right. Actually, everyone defines the cancer from different angle, from the growth, overgrowth, from differentiation problem, and you're talking about the the network, the massage or change. But we actually also want to thinking why, if there's a new system emerged from normal tissue, so that process is is fundamentally important. So actually we, and also actually Dr. Jinsong Liu, we actually try to push the developmental machinery and plus with the evolutionary process. I think that actually could very nicely address some of the questions, like a tissue field, everything. So in such a sense, so we have lots of to discuss. But my question to Perry today, because Perry today is talking about the cancer is a conditionary feature. So my question to you is, so can we think in the cognition actually is an information process? So if that's true, what's the difference between the, like the human cognition and with other animally no brain involved cognition? So what's your idea, and can we quantitatively measure them if that's the case? Yeah.
Okay, so tell me if I understand your question. Your question is, what is the difference between human cognition and cell cognition? And how can we apply that in a meaningful way to cancer? Is that a fair?
Fair, yeah, fair.
Okay, so anybody who's interested in that question should take a good look at Michael Levin's work, because a lot of what he's doing is what is called basal cognition. Basal cognition is cognition outside of neurons and brains. And so Michael's work, Michael takes tadpole embryos, moves the eyes to the tail, and the tadpole matures with eyes on its tail, and the body figures out how to get the signal to the brain, and the tadpole can see out of its tail. Okay. Now, this is really remarkable, because what it tells you is that the tissues go, oh, there's an eye. Apparently that eye wants to get a signal over to the brain. Here, let's make that signal happen. Another thing that he's been doing is he's scraping cells off of tadpoles, muscle and skin tissue, subjecting them to bioelectric fields, and within a day or two, they self-organize into some other organism that is not a tadpole, that grows legs and starts swimming around and can be programmed to do tasks. And these experiments indicate that cells are intelligent, And cells have a self-organizing property that doesn't necessarily have a great deal to do with the genome itself. These are called xenobots, Xenobots. You can go look this up and you can read his papers. Xenobots are not tadpoles, even though they have tadpole genomes. And there's a whole, Jim Shapiro's paper, All Living Cells Are Cognitive, goes into dozens of examples of cells proactively acting on their environment, doing novel things, doing things that never existed before. So Henry, my belief is that cognition is fractal. And fractal is when you have the same pattern on vastly different scales, okay? So there's a tree outside my window and I can look at it from across the street. I could zoom in 10 times, zoom in 10 times, zoom in 10 times, zoom in 10 times. Pretty soon I'm looking at twigs and leaves and the veins in the leaves and the veins between the veins and the leaves. And pretty soon I'm looking at the cellular structure of the leaf and go as far as I want, and it's a branching structure all the way through. Okay, I believe that every cell on Earth is intelligent, and it has some microscopic amount of intelligence that is more similar than different to human thinking. I think we can liberally anthropomorphize biology. And I believe that it is legitimate to think of a tumor as a group of cells that used to think they were part of a guy named Joe and suddenly think that they're on their own, and that it's an identity issue. So going back to Doru's, like, how do you define cancer? Well, another way of defining cancer could be it's a disease of identity. It's when something that used to be part of an entire organism cooperating suddenly says, I want to be me. Henry, give me some response to that answer. How does that sit with you?
So one of the
Henry first.
One of the often asked question people always ask, I said, okay, tell me if cancer cell have any difference compared with the normal cell, right? So that's actually one of the key questions people always thinking, because people kind of believe if you just change epigenetic machinery developmental program, you could make the same cell from normal become cancer. Actually, at the very beginning for initiation this evolution process, which is true, but after finish the process, they always change the system, different system. So that is the key. So it's not just the same system cheating, but it's a different system emerging. So that's what I'm trying to say.
Yeah. I think Jinsung wanted to chime in.
Yeah, I totally agree with you. So, what you see over here.
Pull your microphone closer.
Sorry. What you see here, that's what we use to define cancer. One type of cancer is that immature tissues. All right. So this is period. There is not a question of the argument, because we see these, tissues is immature. We're gonna call it cancer. Okay. So this is something during development. And then, for example, we have a tumor called immature teratoma. So there is nothing wrong with this tissue, except they cannot mature, supposed to grow at the embryonic development. Neuronal tissues now pop out in those tumors. So the tumor will fill with those tumors. So it's not something that you really have to argue, because they will have been using this criteria. Clinical behavior has been defined for many papers, generation by pathologists. That's what we define, call the kids, whether you have a cancer or not. I mean, the immature teratoma, that's a cancer. And the second, group of tumors, those is undifferentiated. And then those cells has to really grow backwards. And then so this process, you can see on the microscope, you can see those changes. So it's not just a polypoid cell, it's a process. So if you think about it, how our human life starts, you have to study those cleavage division. So once you understand how our life starts, I don't think anybody should get into a argument to say how we have a first days embryogenesis all come from. If we deny that, and then there is no base to talk about. And then you can see those tumors. If it does, not come to a uterus, you're going to have a teratoma. So that's what clinically define what is cancer. So after you learn the first 5 days of embryogenesis, and then knows a principle, you sit there, and then everything becomes very clear. So, genes play a role, genome play rules, metabolism play rules, whatever you think there, it's, McClintock, play rules, and then, genome changes, and then gene changes. So there is not much. And then cancer is just recapitulate the very, very basic process of very early stage embryonic development. So most of the people talk about say proliferation, tumor suppression. They forgot cancer is defined by nuclear or cellular immaturity. So this is what we use to diagnose cancer. It's not complicated.
I want to highlight Erwin Schrödinger in his book What is Life? He defined this term neg-entropy, negative entropy. And it's an attempt to express the idea that organisms act on their environment instead of just passively being acted upon. This is one of the central ideas in Jim Shapiro's concept of natural genetic engineering, that the cell is not just a passive recipient of DNA damage. The cell actively moves towards goals to control its metabolism or to adapt to a threat. And I think this is the central unsolved problem in fundamental science. I think if somebody can figure out where neg-entropy comes from, we could solve origin of life, we can solve cancer, we can solve all kinds of things, because in order to even get a cell, you have to have cognition. That is probably a controversial view. But I've been studying origin of life for 16 years, and I think most of the origin of life researchers have gotten this backwards, just like most evolutionists got evolution backwards. And so I actually think that cognition is the central question here. And what we're trying to ask ourselves is, what is going on when a cell decides to become cancerous and take over its own evolution rather than following the program that it's been given? Which again goes back to some of the definitions that we've been talking about cancer. So I'm curious what the rest of you, how you have investigated this question.
I may, at least the evidence that we have collected in our laboratory and other people have collected in their laboratories indicates that a cell is not cancer. A cell there is no such a thing as the cancer cell. People talk about the cancer cell, but each time that you put a cancer cell in contact with normal cells, it normalizes. So where is the cancer cell?
Well, okay, so Michael Levin figured out how to induce cancer in tadpoles with
he has not.
Fields and then reverse back to normal.
I have to go back to Dr. Liu in this case. There are people who talk about cancer and they never seen cancer. And as we agree with Dr. Liu, it is the pathologist that decides whether I have or I don't have cancer. It's not the molecular biologist, nor the cytologist. So cancer is a tissue-based disease. Practically speaking, Dr. Liu tells you whether we have or we don't have cancer. The problem that I don't understand is that at the same time that Dr. Liu says this, he proposes that the problem is a cells problem. So this is the contradiction that all of us are running into. So perhaps I am not realizing that I also am talking against my own ideas. Well, but Dr. Liu says cancer is a tissue-based disease because only he, and I agree, only pathologists diagnose cancer. And then he goes and talks about what happens with the tetraploid and the polyploid cells.
So there's an old saying from the 1980s where some judge said, I can't give you a dictionary definition of pornography, but I know it when I see it.
Yeah, that's right.
Isn't it fair to say that cancer is a lot like that?
It's very simple. Dr. Liu tells you this is cancer or this is not cancer.
Okay, so can I?
Go, Jinsan, go ahead.
Carlos, this is a good discussion, all right? So first of all, agree, and then say this is what the pathologist tells you. Define what is cancer, what is not cancer. Hopefully we agree on this point. Okay, what I said, in first group of tumor, that's all immature tissues. So this is how all of the cancer immature teratoma is defined by, under microscope, see the volume of those immature tissue, we call the benign or malignant. So this is the first criteria, okay? So second, I call the polyploid giant cells from mature. It's not a cell, it is a process. I call the giant cell life cycle. It's a differentiation process to convert a mature cell into immature embryonic blastomere like the cell. So polyploid giant cell just a part of the process you can morphologically identify. So it's not a cell, it's a process, embryonic process. So it's same, it's not come to unicellular. Although at the end of the day, we can look some cancer cell, now this is the results, you can generate cancer cell, this is fine, okay? But whole thing, how cancer is defined, it's a process. Okay, first the process, you have a good embryonic process, and then development, you stuck over there, you cannot mature, that defined amount. The amount of tissue is a defined tumor behavior. Second group is the same embryonic process, except start from mature tissue, and then they cannot go to developmental field like a uterus. And then because you stuck them, I totally agree your field theory. In embryonic development, and then you cannot go to a uterus like a normal egg, normal blastocyst. So you stuck over there, but the process, it's embryonic process. It's not a cell. Is that clear?
Could I put more to add up? So Carlos, so it is a social, it's a tissue phenomena. But the tissue phenomena, when they become formed a totally different system, there is an evolutionary process involved. So if you agree evolutionary involved, there must involve inheritance. So that's a basic, so the angle we are thinking about. But we know, even though the cancer cell the genome change, but that necessarily mean every cell will have genome change will become cancer. So that's a highly probability process. So that's we all talking about this process. So that's my question. But I really want to go back to this subject, which is cognition, right? Because so that's what the Paris want to answer the question. So maybe some other people will have this section to really discuss what cancer is. But my question to you, Perry, again, is this. So if you're thinking the cognition is initial, even before another force, so could that actually increase the difficulty for you to explain why the cognition, which is in our mind is much higher order of information actually at the very first place. This, secondly, if your thinking is fractal, you're thinking everything could be this way. So therefore, for the higher animal brain, is that the quantitatively more the unit of such information, or what's, so what's the, so it's very difficult for other people to digest, even though it's quite interesting to thinking that is the first layer.
Well, so one of the most basic concepts in information theory is that you can turn any information into ones and zeros. In other words, you can turn any kind of information into math. Like, that's why you can see me on your video screen right now, and you can, because my picture and my voice has been turned into mathematical symbols and then reconstructed on your screen. But one of the most basic things about information theory is that it is not possible to quantify meaning. So you can encode a message as ones and zeros, but you cannot reduce the meaning of any message to ones and zeros. And I think this is one of the most fundamental problems in science. And this is why cognition has been resisted for so long. Because I do not think cognition can be reduced to reductionist terms. I do not think consciousness can be reduced to math and physics. I think it is another kind of entity, and I am far, far from the first person to say this. There's been philosophers talking about this for thousands of years, all the way to the present. And so one of the things that this means, so Carl Woese talked about physics envy, and he said that the biologists have been jealous of the physicists because physics is so exact, and they have tried to reduce biology to physics and chemistry. And biology is actually a field with its own set of properties that are not present in those other fields, and it needs to assert itself as a unique discipline in the world. And I don't think a truer statement could be said. And so what this means is that I think a lot of scientists have an addiction to certainty that you have to let go of. So for example, there's not going to be any one perfect definition of cancer. There's not going to be any one perfect definition of life. It's going to be ambiguous. As soon as you embrace the ambiguity, it becomes very freeing, because then you realize that you could have any one of 10 useful definitions, and each one of them could be useful in a certain context. And it gives you respect for other professions and colleagues in other fields. I think one of the best things about this conference is that we've got, well, let me look at my screen. I've got a practicing clinical oncologist, Doru. I've got Henry, who has this whole genome chaos thing. I have Carlos. We have Jinsung, who's a pathologist. I don't know very many pathologists, so that's great. Who else is on here? I've got Christian Linhart, who is a computer science guy. I've got Michael Turpak, who's in real estate. I've got Jim Shapiro, who's a geneticist. Tao Wu, who I believe is some kind of cancer research, but I'm not exactly sure what it is. I mean, we all need to figure out how to talk to each other.
Well, if I may, I totally agree with you, Perry, that biology is a unique thing and cannot be translated into physical and chemical things. You referred before to the author Schrödinger. Schrödinger he was a genius, but he was a genius in physics. Right. And physicists have told us, oh, as you know, and a lot of them made a lot of money saying this, they are going to tell us who we are by putting a card we'll have the ones and zeros in a card, and we are still waiting for that.
Yeah, we'll be waiting a long time.
Right, and IBM told us that they are going to tell us how to make a diagnosis of cancer by using Watson, and we are still, I mean, they decided, forget it. Now, until people realize that biology is a unique science and adopt new ideas about it, we are going to come back, whether you do it using information, which is, as you are well aware, a very, let's say, controversial terms. There are people who discuss what is information, depending who you read.
Yep.
And people, of course, they are going to, unfortunately, muddle up the whole field because they are talking against each other or through each other.
Well, people have to define their terms. You know, I got in a debate with a guy about 2 years ago. It took me 6 weeks to get him to define randomness. Well, I know why. It's because I was getting ready to nail him to the wall with a definition that didn't make any sense, right? And it made sense from within a particular thing that he was trying to do, but it didn't make sense in a larger context. And so, well, so you're going to have problems like that. So let's keep pushing this forward. What are some other questions? Does anybody have any questions about my presentation about codes, cognitions, and physical chemical layers, or questions about, I don't know, this might be an interesting thing to discuss.
We like to get this clarification, because I think you think that code is really biology, and then cognition is really more like cognitive sciences. So, you know, the three questions: how from nothing came something, so the Big Bang question, then from something without inert, without life appeared, and then from something that was alive, intelligence and cognition appeared. But here you put the things, you reverse them. You said, you know, we should go back and start from the highest level, which is cognition, and go back to life, which is the code, I guess.
Well, no,
go back to physical chemical.
Well, genetics is code. I think life is cognition.
So that was my question. So you're putting together life with cognition. Like, this is Dr. Hang's question, because you're really putting a cell on the same level with the brain, basically. So this is where we have discussion, you know.
Yeah. So the physical layer. So physical chemical laws. They're universal. They're the same everywhere. Okay, and then codes are symbols and logic. And I think mathematicians have a very good grasp on what logic is, because like you have Euclidean geometry, you have hyperbolic geometry, in mathematics, you have to define what system you're in based on the axioms, and then, you know, so you can tell us everybody's location in the world in cylindrical coordinates or rectangular coordinates. Okay, so that's the layer of logic. Okay, cognition is the ability to make choices, and all life makes choices, and so we have a narrative in Western science that says that you know, we had the Big Bang, and then the chemicals eventually turned into codes, and then the codes eventually turned into cognitions. But as an engineer who's been building things for 35 years, I've never seen anything get built that way. And this is kind of like the elephant in the room. It's what everybody's arguing about in the
I'm sorry. We're having some feedback on your audio, and I just want to make sure.
On my audio?
Yeah, it seems like it.
Okay, I'll be back in a sec.
Sorry, everybody. I just want to make sure that we can understand Perry well.
I can put on a set of headphones and probably fix it really easy. So just here. Okay, is that may be better.
It's it seems like it's yeah. Let's see if that helps.
Okay, so I insist. So we have gotten cause and effect backwards in science. Everybody is trying to solve a cognition problem with chemicals. It's not working. It's not going to work. It can never work. It's like editing a book with battery acid. Now, can you edit a book with battery acid? Well, sort of, with an eyedropper, or maybe if you're willing to dunk an entire page and delete an entire page at a time, but it's the wrong tool for the job. So back to you guys. Let's hear from
Carlos has something to add.
Yes, Carlos.
I agree wholeheartedly with you, especially because at least you confess the problems that you have faced.
I had a conversation with Andrew Briggs, and Andrew was talking about he's a physicist at Oxford, and he was telling me why he was such good friends with Paul Davies, who you guys heard from at the conference, and Andrew says, Paul said to me one time, Andrew, you know what I like about you is most scientists are interested in answers, and you're interested in questions. I think questions are much more interesting than answers. I think ordinary scientists obsess about their answers, and great scientists are obsessed with questions. And great scientists are always looking at, what do we not know? I believe that one blade of grass is 10,000 years ahead of any human technology. And when we finally, there's something very liberating when you finally just accept it. It's like, this thing is so much bigger than me. This is so much more amazing than me. I cannot reduce this to chemicals. There is a mystery in this. This is and I am free to explore the mysteries rather than being confined to the corset of some ideology in which I am allegedly supposed to make a living.
But there are two deep mysteries here. One deep mystery is cognition. The other deep mystery is the cell, the life. And you're basically making from two big mysteries one big mystery.
Yeah. No, actually, I'm making, well, if in my slideshow, I think 5 mysteries are one. I think origin of life, origin of information, consciousness, evolution, and cancer are one question, and the question is cognition. Now, we don't know what it is, except we all know what it is. We don't know how to define it scientifically. We don't know how to reduce it to any one definition, but we all know it when we see it. It's like pornography. We all know it when we see it.
I find this conversation absolutely fantastic, and I hope that we'll have a chance to pursue this further. But unfortunately, I have to go. I'm flying to Europe in 2 hours, so I have to catch a plane.
Fly safe.
Thank you
Stay
very
healthy.
much. I'll come back.
Okay.
When are you going to have these type of meetings again?
Well, there's Tana.
Go into your chat. If you go into the chat right now, you will see a list that is the schedule of all future Q&A sessions. Good. I would honestly, if I were all of you, we will send out reminder emails for this. Copy and paste that into your notes or something so that you have it all available. But we will also be sending like 30-minute heads up ahead of those meetings as well.
Super. Thank you very much. And I'm sorry again. Congratulations to all of you. You are very fortunate to have questions to answer.
Okay. I think Jinsung Liu had something to say.
I would say, probably would be better for your definition is to define the level of the cognitive, because there are different levels of cognitive, right? If you talk about the virus, right? They can evolve and kill all of us. They're clearly very smart or cognitive, right? But this is different from our brain when you think, right? So you have to give a clear definition. Otherwise, people will get all confused, what kind of cognitive, right? And then second, the code. You will probably also need to define what the code, because in your code, you talk about the genetic code, say, or ATGG, whatever, this is something that genetic code that people get. But, when I talk the code, I talk about how to generate a life, say embryogenesis. So,
well,
yeah.
So
clear.
So on the,
yeah.
Okay, on the definition of code,
yeah.
I had to really sharpen my pencil on this, because if I'm awarding a $10 million prize and I have the wrong definition of code, I'm going to end up paying $10 million for a bunch of garbage, and then my career is over, right? So
What's the definition of code?
Okay, code is symbolic information transferred between an encoder and a decoder. And if you go to naturalcode.org, you can see our prize announcement. You can see all the specifications. You can read submissions that have come in and all of that stuff. This is from Claude Shannon's work in 1948. Most any electrical engineer will know who Claude Shannon is. He's the father of the information age. And DNA transcription and translation is identical to Shannon's model. So a genetic code table is exhibit A of a code. It's just like Morse code. It's like, well, A is, this dot, these dots and these dashes, and B is these other dots and dashes. So it's essentially the same thing. And so what I realized was that the ability to assign a symbol to a referent is one of the most fundamental questions in science. So in the genetic code table, GGG is code for making glycine, and AAA is code for making glycine, lysine. There's no law of physics that said that that's how the table should be constructed. It's just like there's no law of physics that says what the Morse code for SOS should be, right? It was chosen arbitrarily, and that is a indication that there is cognition involved in having made the choice in the first place. And so we actually have a very clear definition of code. I do not have a perfect, absolutely clear definition of cognition. I have a know it when I see it definition. But in code, we have it absolutely crystal clear. And in fact, I have never had a serious scientist challenge us on the way that we've defined the prize. And George Church was actually instrumental in helping us clarify a few things in the prize specification. Does that help you out, Jinsung, a little bit? Or Doru? I saw Doru unmuted.
Yes, it helps us, but I think it's a slippery slope here. And you're pretty much identifying this symbolic information transfer between an encoder and a decoder with cognition. And I'm not sure if mind is only that.
Well, okay, so
something as simple as a code.
So I don't think this is mind.
Right.
I think this comes from mind. I think codes always come from cognition, but codes are not cognition. Like there is no cognition going on inside your computer at all.
Right.
It is computation, that's all it is. But cognition defined the parameters of the computation, right? So cognition defined an operating system. There's a term in Jim Shapiro's papers, he calls it a control regime. And what it refers to is the idea that when the cell does natural genetic engineering, there is a framework that it is adhering to that we do not understand, but is somehow implicit in the system. Doru, does that clarify things any for you?
You defined, life as a volitional, cells as a volitional Turing machine.
Mm-hmm.
And you use both cognition and volition with, different nuances, but both belong to mind.
Yes, they do.
These are not different mind aspects, and you simply say that the cell is a mindful entity.
Yeah, I believe that's true. I believe that cells, a cell is more like a miniature human being than it's like a molecule or a rock or a snowflake. And I think when you're fighting cancer, you're fighting the Viet Cong. And when you,
I agree 100% with that.
When you administer chemotherapy, you just napalmed the Viet Cong village. And if you don't kill 100% of them, the 2% you didn't kill are absolutely pissed off, and they're coming at you with everything they can: machetes, guns, knives, bombs, acid, anything they can think of.
This is true. I've been seeing this many times.
So I have a quick question. So whether Perry or Jim can help me out this one. So should we just simply say the condition themselves is a package of the life? The first one. And secondly, is this evolving of the capability is correlated to the the life tree of life?
Okay, hang on. These are great questions. So say the first one again. Let's take that one.
I said whether or not we just simply saying the cognition is the package of the life, no matter what type of, like the Jin Song said, okay, virus have their own package of the capability, and the human, for example, the example is like Down syndrome. They just have a tiny piece of the chromosome. The intelligence immediately just have different level in terms of potential of training. So can we just simply say the nature themselves just constantly just try and error to create so many different package, and then somehow the selection like a one-way filter to just hold the complexity, not allow them to go back to in such a way, so we can see such so colorful different beings with different level of cognition. Is that fair to say? So that's the first question.
Well, yeah, okay. I think what you were saying is, tell me if I'm right. You're saying that life has the ability to modify itself and to modify its own capabilities. And so any biological organism is a package that is a sum total of the history of the self-modifying cognition to date. Is that it? Am I understanding you?
Basically, what I try to say is the cognition maybe is an unseparable feature of the package for each different system. Is that true?
Well, if it's alive, yeah, right? Like you can kill a cell or you can kill a mouse and you can study what's left, but the life is gone, right? And so now you're just studying a machine that is no longer running.
So my second question is, if that's the case, during the evolutionary process, whether or not the cognition, this part, maybe they actually directly correlate with the genome or gene or something, or just separate. So how do you think?
Okay, so I think that the genome is a trailing indicator of what the cell is doing. I think if I'm going to use a computer analogy, which is very crude, it's very limited, okay, but I would say that the cognition is the processor chip, and the genome is the hard drive. And so you have all of these inputs going into the processor, and people are typing or Skyping or whatever they're doing, and all that's going on. And what gets written on the hard drive, like when you get done and save the program, that's essentially the genome. And of course, processors access hard drives to pull information off. But I think one of the biggest mistakes in the history of biology is assuming that the genome is in charge. The genome is not in charge. The genome, the cell is in charge. The total entity is in charge. I think the selfish gene is one of the biggest mistakes in the history of biology, because it doesn't work that way. Engineers know this. When I got into this field 16 years ago and I started reading books, I was horrified at some of the stuff that I found. Like if you went to the bookstore and bought an evolution book from Jerry Coyne or Richard Dawkins, it was like a work of fiction. And Jim Shapiro gave a talk at Fermilab 10 years ago, and somebody asked him a question about Richard Dawkins, and he goes, "I think Richard Dawkins lives in a fantasy land. There's no such thing as a selfish gene." I think Dennis Noble has defined this very well in his principle of biological relativity. He says there is no privileged level of causation in biology. You can't look at any one thing and say, oh yeah, this is where it starts. Because he studied the cardiac rhythm. And he's like, okay, what makes the heart beat? Well, if you know anything about a digital watch, there's a crystal and it makes these little vibrations, and the vibrations get divided up and they get divided into minutes and seconds. And I believe when he first started trying to figure out the cardiac rhythm, he was sort of kind of assuming that the heart must work that way. Turns out, no. It's got these 3 different feedback loops, and they are affected by all kinds of things, and they're redundant, and there isn't any one place where it all starts. It's not like, a clock with a little thing that's ticking and then everything is getting divided like that. It's systems within systems within systems within systems. So to an engineer, life runs on a completely different operating principle than a computer, which is why these analogies are very crude. And we have to completely rethink this whole thing from the bottom up. And the fact that we've spent $250 billion on cancer and not really gotten very far is one symptom of the problem.
I agree with you, Perry. I think one of the central problems in biology and cancer research, they think it's a gene and a genome, is a driver, but actually it's a cell is the driver. Because cell is the one as an entity, they have to adapt the whole process. So cell include membrane, right? And also various organelle structures are really the one that can drive probably the membrane. Even more important, because without the membrane, you're going to have no life. And then all those genomes come out later. So I think it's a 21st century biology since discovery of the molecular biology that made driver and passenger reverse. So because you constantly look for gene, because your first gene, genetic code and a life, and then now it comes to the genome, right? So I know you like Carl Woese. Actually, Carl Woese was my favorite when I was a graduate student, because I worked for Norman Pace. He's a good friend of Carl Woese. So I know Carl Woese from very beginning, but especially like his new biology, I have read, because Carl Woese is one of the great thinkers. He thinks, central biology for molecular biology, pretty much for it's a process. Probably you have go through this process, but largely in his view, it's already done. It's already done its job. It's time to move more, higher level, like a cell level, and then to really recognize what is life, what is biology, and then he think those 21st biology is simply too similar to this the 19th century's physics. It's already done its job and made a lot of discoveries. But to move things forward, like a fundamental principle of biology or fundamental principle of cancer, you have to really think about holistically what is really life, and not only about single cell, but you have to look for higher level, like a human, right? Go to higher levels to say, how are you going to put all this together to generate something as complicated as humans, as a cancer, right? Cancer in a human. So I, totally agree with you regarding the genome is the driver or there's a passenger issues. So I think the biologists have got the whole thing reversed. But it's a process. I think nobody can, avoid this process because everybody get fascinated about all those genes in the genome, and then it's time to move to a higher level.
Well, I've taught thousands of entrepreneurs how to do advertising and start businesses and do marketing and especially on Google and Facebook. And I tell, so like I have a lot of friends who they sort of kind of know about the Evolution 2.0 project and they're a little intimidated by it because they're not biologists. I say, if you've been running a small business, if you've been advertising your business on the internet and dealing with all the competition and everything, you probably understand evolution just as well as most biologists, okay? Because you're living the life of cognition, mutation, selection, competition, just like anything in any ecosystem. In fact, business is just a fractal expression of biology. Why? Because money and commerce is how all of us eat, right? So the principles of evolution in business are absolutely identical to what they are in a pond, which is absolutely what they are identical they are in your elbow. And any business person knows that business is really much more about cooperation than it is about competition. I mean, sure, if you own a pizza restaurant, you've got competitors. There's like one down the street and there's another one 2 blocks further. But how many people do you cooperate? You cooperate with the waitresses and the cooks and the delivery guy and the vendors and the water and the utilities and the building and the landlord and the sidewalk and and the radio station, right? And so it's one of the reasons I'm an admirer of Lynn Margulis. Her documentary Symbiotic Earth is beautiful. You guys should watch it if you haven't. And so I actually feel like my business experience has always been a pretty helpful guide in thinking about cells, cancer, evolution. How many of you have had somebody in your department who's cancerous? Like, as in, they start fights, they pit other people against each other, they're doing their own agenda. They tell Henry one thing, they tell Jinlu something else, they tell Doru something else. They divide people against each other. Like, it's not a coincidence the word cancer in the organization is a common metaphor in the human language because it's the same thing.
Barry, I would like also to make another comment which you may like actually. So this idea of separate worlds between the cell, the mind, the physical world, I think goes back to Aristotle and then goes through Descartes. But
yes.
Other traditions, for example, we have here 2 Chinese people. If you go there to the Taoism, or if you go to the Indian tradition, the Vedanta, you'll see there that the cosmos was alive, basically.
Yes.
So for them, not only the cell had a mind, but also the so-called inert objects like a stone, it had a mind. So it went down to the origin of, the Big Bang, the origin of the whole universe, this discussion about what has a mind,
Well, so it's never seemed apparent to me that rocks could think. Like one of my favorite little jokes is, what's the definition of nothing? That which rocks think about. However, having said that, so like I'm not a pantheist, for example. However, I think it's really interesting that like the double slit experiment in quantum mechanics shows you that the outcome of a quantum event is determined by the observer, okay? And that is another one of these very fundamental bottom of reality things that everybody struggles and wrestles with. Okay, if it's true that even a quantum event is not determined until there's observer, it means that the division between subject and object, where subject is the ability to observe and be an observer, and object is just being a rock. The fact that that distinction goes all the way down to the quantum level, and that, like, Howard Petty has been writing papers for 60 years explaining that that division is at the cellular level, that a cell is a subject, that a cell is an observer. And then combine that with the fact that all religious traditions are about action and what the world should be, not merely what the world is, whereas modern Western science has tried to tell everybody that there is no should. Well, it doesn't have the right to tell anybody that until it solves its own problems. How on earth can you pronounce that there's no purpose in the world when you can't even create a cell in the lab with $40 million?
We have a comment.
Expanding the discussion, you know, I think it's important to to have also this. You're basically coming back to what the discussion were like 25 centuries ago.
Yes, and Eric Kolker, if you want to come off of mute, I saw that you have a comment about the way that we are referring to cancer. If you have the ability to come off of mute, go ahead and do that. If you can't, yep, there we go.
Sure, Perry, one of the things that stands out is that great to see you, Perry. You're referring to cancer in very militaristic terms, that it's the Viet Cong and, you know, you have to attack them very hard. And so if a cancer cell...
Oh no, I'm not saying that at all.
Oh.
I'm saying that when we treat it that way, we get the Viet Cong.
Right.
I'm actually suggesting we need to treat it completely differently. I think if we'd gone in and figured out how to negotiate with those guys or something like that, we might have avoided the Vietnam War.
Right, because you're saying that the cell has cognition, it assesses the environment. If the environment is threatening, it diversifies, and therefore that increases in order to increase its survival. And if you change the environment, then the cancer has much less pressure to diversify. And one of the things that stands out is from a psychological perspective, when people receive psychotherapy, when they've already been diagnosed with cancer and they receive psychotherapy, they have longer survival rates than people who do not receive psychotherapy.
Eric's a psychotherapist, by the way. I've known him for a few years. So yeah,
and that just is an indicator to me that when we change the psychological environment, and of course the psychology imprints on biology, because if you're going into fight or flight mode because you're frightened or you're shamed, that's going to affect the environment around the cancer. And that if we look at the psychological environment that the person is living in, as well as the physical environment, and we look at how can we change the psychological environment so that the person feels less threatened, and then by extension, the cancer has less stress on it, that will decrease the hostility in the environment, that will slow the tumor growth. And my perspective is that, you know, you need to address both the psychological and the physical environment in order to slow the cancer from changing so much.
Well, Eric, try this on for size. How do we get cancer cells out of fight or flight? What if we framed cancer as a psychological question with a cognitive entity?
I spent the entire weekend, I wrote a letter for you, I'll send it, showing how when people experience psychological injuries, their risk of cancer doubles.
Well, my dad got cancer at age 41 in his kidney after he'd been through a year of hell.
Yes.
Okay, so so my mom went bipolar about 2 years before that. And all of a sudden, every day I come home from school and the house is bedlam and everybody's arguing with each other and my mom is crazy. And you get sucked into an argument like 2 or 3 times a day. And you don't know whether mom's going to be in a good mood or a bad mood or whatever. And had no idea what was going on. My dad was a minister, and they expected the pastor's wives and the pastor's families to be really well behaved. And so they started putting pressure on him, like, you better get your wife under control. You know, pastor's wife's not supposed to be acting like that. He had no idea what the problem was. He started casting about, looking for answers anywhere he could find them. Eventually got her in front of a psychiatrist. The psychiatrist says, well, your wife has bipolar with mild schizophrenia, and he prescribed medication, put her on medication. The next day, his boss at church found out that he'd taken her to a psychiatrist. Psychiatrists were not allowed at our church. And my dad got demoted, and a week later, an announcement in front of 2,000 people that Bob and Betty have had some problems and Bob is stepping down from his position. And it was like this really humiliating situation. And he spent the next 9 months getting in his boss's face saying, my wife isn't in some moral degenerated condition, and she's not in rebellion or sin. She has a medical condition. She's on medication, and we're solving this problem, and you owe my wife an apology. And she got that, they both got that apology, and my dad got reinstated. And a month after he got reinstated, he got blood in his urine because he had cancer in his kidney. And I think, and like it was like our life was a living hell for a year. I don't have any question that that had a lot to do with the fact that my dad got cancer. I don't think there's any oncologist who would disagree that stress has a lot to do with cancer. The Paul Davies presentation the other day got into that. And so I think we have a question of how do we get that psychological health all the way down to every last cell in our body. And when there's a runaway condition like you have with a tumor, is there some way that we can convince those cancer cells that, hey, you know, everything's okay. Maybe you could just go back to being like one of those regular cells. And I'm speaking in very anthropomorphic terms here. I hope you'll forgive me for that, but I think that's what we have to somehow do. So let's hear from all
aspects are very important, and there are studies done on mice that are put in an enriched environment in which they're not alone in a cage, but they have friends, and the cages are larger, and the survival with different type of cancer doubled actually. And it's been shown also in patients that are in fact married, they live longer than they're alone and they don't have a support. So I think it's extremely important.
Actually, the survival rate for being married is larger than the published survival rate for chemotherapy. I'll send you the reference.
Yeah.
And, you know, if you're in, and that's just the binary thing of married versus non-married. It doesn't say anything about a highly supportive marriage versus an emotionally disconnected marriage. And when people are in a peaceful marriage compared to a hostile one, hostile marriages, you know, have immunosuppression and much more inflammatory markers in there. So, you know, there's, you know, the impact of healthy relationships on tumor growth is very substantial.
Yeah. So there is a group I just share with you. So the study showing if the breast cancer 5-year survive could increase change about 20% if you have some relative take care of you in the sense. So those actually is over any oncogene, any biomarker. So there's no such a magic. But I think now some of the major cancer centers, they have the psychological or the exercises or caring in such a way after and before the major treatment. So this is encouraging. So there is a group of people that promote the complex science and the holistic treatment. From Duke, from all the school, they have some very interesting results. For example, when the technician checking the patient use the machine to scan everything. So if you hold the patient's hands, this group of people much better recovered than you just doing this experiment. So the human is magically very not just the tissue, not just organ, but is the individual. So this is very important leader.
One of the most successful cancer treatment was from China, use retinoic acid to differentiation rather than killing. So those was proposed by Barry Pierce in 70s. They used to have differentiation conferences, therapy conferences during those years. But since oncogene started, everybody moved to the targeted therapy. So maybe it's a really time to rethink of those cells really can be differentiated. One of the reasons I've been thinking about this, why differentiation has not been working very well in large solid tumors, because you have those treatments, they have a very small window. Actually, you can differentiate, because if you pass these windows and a tumor already becomes stabilized and lost the stemness, you really cannot really do differentiation therapy. So because we really did not understand this process, how the tumor really formed. So those genomic chaos, the whole reprogramming, is something I think everybody has to pay attention, because you do have a therapeutic window there. Not only becomes bad, worse, and then you can also put them behind little nice guy become normalized. Okay, so but anyway, I have to go now. I have another meeting. So very nice talk to you. All right, thank you. All right, hope some other times we meet again. Okay, all right, bye.
Thank you.
Bye.
Yeah. I want to pick up on, I believe it was what Henry was saying about the technician just holding the person's hand. And this fact is extremely well known in psychotherapy. The quality of the relationship between the clinician and the patient is a much better predictor than the technique. And even in psychiatry, the quality of relationship between the psychiatrist and the client has a bigger impact or equal impact than whether the person then gets an active pill or a placebo. And so this is one of the, since we know the quality of relationship between clinician and patient is so strong in psychotherapy and in psychiatry, one of the huge questions I have is the quality of relationship that the oncologist or the clinicians and that the patient experiences with the treatment team, is that routinely measured? Because if you feel that the clinician is warm and caring, and that puts the person in a state, they're going to feel more relaxed, they're going to feel safe. But if they feel that the clinician or the clinical team is arrogant and dismissive, they're going to feel anxious. And so the interaction between clinician and patient is going to have an impact on, how stressed the patient feels, how rapidly the tumor grows, how much they respond to treatment.
I'd like to hear what everybody else has to say about that. And there's a lot of you who haven't said anything, so maybe some of you who are lurking would like to speak up. You just unmute yourself and say hello. What other questions do you guys have? Is there anything else?
I think the main question is how you apply this model to cancer care. that's, you know, as an oncologist, that's the first thing that I would immediately jump on.
Well, I can only respond with a question, not an answer. And the question is, how do I get a cancer cell to want to do something else? How do I get a cancer cell out of fight or flight? And how about if I define this as a cellular psychology problem and a persuasion problem rather than a chemistry or genomics problem? What if I use genomics perhaps as a way to find out where the cancer is or what kind of cancer it is or something like that? But like, what makes a cell want to be cancerous? I think we have clues. How would we make it want to do something else? And I'm not prepared to say that I have an answer for that. I just have a different question than maybe most people are asking.
Dr. Liu told us about the retinoic acid, that it's in fact used in a type of leukemia with very good success. And that would be one of the ideas, just to pursue this type of differentiation treatments. But I think it's more than that. And your important question is, what do cancer cells want? Because these cancer cells are just dividing, you know, incessantly, some of them, not in all cancers, because in some cancers, the division is not a problem, but the lack of death is the problem. And what do they want? So maybe if you can negotiate it, you say, with them and give them some part of what they want, maybe you can just keep them under control. And then you enter into the get and buy model in which you're into a chronic disease, you know. That's what Dr. Gettenby wants to do.
I had a cancer researcher tell me once that cancer cells like to be talked to. And she and anybody else would realize that most people would think that's a nutty thing to say. But I think she really was onto something. You know, Barbara McClintock, if you read, I think it's the book, A Feeling for the Organism by Evelyn Keller, Barbara McClintock said, you know, that plant knows that you're standing there. And she had this view of nature that was very different than most of her colleagues. And this is why it didn't surprise her when a corn plant turned out to be completely able to restructure its own chromosome in real time. Or there's a really interesting book. Is it called like The Hidden Life or The Secret Life of Trees? Very interesting how trees are in communication with each other and they look out for each other, and the good ones take care of the sick ones. I think we have to have a completely different view of nature. And it's not just biochemistry. I just saw Adi Pras came on board. Adi is a chemist in Israel, and we've had great conversations. And he's got a book called What is Life, where he talks about the purposeful ways in which living things behave. And, you know, he's trying to approach this from dynamic systems chemistry.
He's here.
Yeah, well, I saw him come on board, so I thought I'd bring him up. Maybe I could get him to come out of his cave. And so, you know, even like I think Adi has a view of chemistry that's even probably much more advanced than most chemists. So, Adi, you want to chime in?
Well, yeah, I think we're talking about one of the most exciting questions, not just in evolutionary theory, but in science generally, and that is what is life, and to understand what is life, we need to understand the connection between living and non-living things. And it's amazing to be able to say this, but with all the amazing advances we've had in science over the last, let's say, 100 years, physicists have been able to dive deep into the atom and way out into the universe to the beginning of time. But the stuff all around us, you and me, trees and whatever, we still don't understand the connection between that stuff, that material stuff that's around us, and dead stuff, inanimate stuff. And it goes back to very deep questions. Aristotle, is the world teleological? And then 400 years ago or something like that, the modern scientific revolution said, no, guys, it's not teleological. Nature is objective. But there's a problem there because science is based on empirical evidence. And if you see a lot of material stuff that behaves teleologically, then it doesn't, you have to kind of figure out how that fits in with the objective point of view. And this is a little bit where we're stuck. But what I want to say is, just very briefly here, I mean, it's very clear from the work of the last, several decades, but as Perry said, going back to Barbara McClintock, it's clear that life is cognitive and the bacterial cell is cognitive. Jim Shapiro just sent out one of his latest papers just from a couple of months ago. And I mean, the evidence is overwhelming. So cells, that little blob of protoplasm, so-called, is very, very social, very cognitive, knows what it's doing, talks to its neighbors, plans how to do things, et cetera, et cetera. So that's beyond question to my mind. So it's not just when we cross the road that we are very directed in our actions, being careful to do that. But cells do the same thing. But when we come down to molecules, when we go back a couple of layers down, suddenly the world is objective and we don't say molecules behave in that cognitive fashion. So here is the big question. Where is the Rubicon and where was it crossed? And was that process from molecules to the cell a gradual transition, or was it actually a Rubicon crossing, a major step? So this is an interesting question, not an interesting question, more than that, a dramatic question that is still seeking an answer. And I would just, in the few minutes that I have here, I don't want to hog all the time, I want to say that something quite dramatic has happened in chemistry over the last half a dozen years. A new dimension of chemistry has suddenly been discovered. If chemistry till, let's say, the beginning of this century was, let's call it thermodynamic chemistry, chemistry, let's say, like on the surface of the earth, I'm just giving that as a visual, all of a sudden we've discovered that there's another dimension up there that hasn't been looked at, and it's dynamic chemistry through systems being able to be persistent because energy is coming into them. So you can have systems that are stable in the sense of being persistent over time, not because they're thermodynamically stable, but because energy is coming into them constantly. And my metaphor for that is a fountain. A fountain is not a stable entity, but it's there, it persists as long as the pump is doing its pumping job, right? Mm-hmm. So there are chemical systems that behave like that. And here, I think, is the essence, the beginning of understanding what life is. Life isn't just a bunch of molecules that have mixed together. They're in this excited dynamic state, a little bit like if you want to think of a juggler juggling several balls. It's a very different state to that juggler standing next to the several balls on the ground. So when people try and mix stuff together, they're not going to get a living things, even if it's all the right stuff. You've got to get that dynamic state in action. And that is something we're just beginning to figure out, because it's only been a few years that chemists have really discovered that there is such a dynamic state. So I think if you like, this new dimension of chemistry may begin to characterize where that life is really just a particular example within that new dimension. And I think, you know, that's as far as I should go at this point.
Well, that's beautiful. And like, I think it's good for people to simply know that there's a whole branch called dynamic systems chemistry that has discovered another dimension that is only beginning to be explored, because once again, at least you know what the questions are, even if you don't know the answers.
Yeah.
Perry, I'd like to point out that you actually answered Doru's question, right? Doru said, you know, what can oncologists do? We were talking about how, you know, how to make this knowledge about decreasing stress on the person, and that improves cancer outcomes. And then you said cells like to be talked to. People like to be talked to. And what people really want is the opportunity to dialogue with their care providers, because you're in a power imbalance. You got these oncologists with these, you know, super high-powered brain cells and all these $10 words. And then you got this electrician who's laying in bed in a hospital gown, and they feel this power imbalance very acutely. And they can't question this incredibly smart doctor because they feel so inferior. But if you measure the sense of teamwork between the client and the clinician, and you know, you ask the client, you ask the patient, hey, how's the sense of teamwork? Am I explaining things clearly? What are your goals? Are we helping you achieve your goals? Does my approach work for you? Is there something about my approach that you want to change? If you flatten that power imbalance, then the person feels that they are talking to their oncologist or their physician, and then they feel less threatened. And then they feel that the oncologist understands what their goals are and how to help them achieve their goals. And when we do this in psychotherapy, the effectiveness of psychotherapy doubles. And psychotherapists, this is our full-time job, is to listen to people. It's not to, you know, study the Journal of Oncology. It is to listen to people. But by golly, when we hand them the scales and we ask them, hey, can you give me feedback about the teamwork that you experience with me? And then they start giving you feedback and saying, actually, you know, you don't understand this particular goal of mine. That flattens the power imbalance. And I found my clients got better. And actually my office emptied out because they got better faster. So now I had a separate problem, but I want to, you know, Doru's question just hangs at the back of my mind. What can oncologists do? And you know, we can unpack this later, but the takeaway here is if oncologists and the treatment team got into a pattern of routinely asking the patient, what are your goals? Are things clear for you? Are we helping you achieve your goals? Which of our interventions fit with your goals? Which ones don't? Then the patient feels heard. He's being talked to, or she is being talked to. They're less stressed. The environment, you know, all the way down to the cellular level is changing because they're relaxed. They're not threatened. They're not anxious. And you know, it's actually extremely simple to do it's quite simple to do to, you know, start engaging and asking the patient, how do you feel? What are your goals? How can we help you?
Good. Let's hear from some other.
Great if it'd be so easy, you know, the things are more complex than that. So 2 years ago, I had the same hypothesis, and what we did 2 groups of patients, and we received funding from the American Cancer Society in order to see if we approach the patients in this type of humanistic / spiritual way. We're going to improve their survival. Because when the patients are sick, the meaning of life, it's important for them, and the meaning of life will be also transferred in the strong spiritual link. And we did a randomized study, and half of the patients will receive information about their disease, and half of them will do prayers, meditation, and we're hoping to show that by doing that, we can improve the survival. We improve the quality of life, and this is very important, of course, but we're unable to show that the survival is improved. So it is extremely important, of course, for any cancer doctor to talk to their patients, and it's important at all levels, and to continue to talk even when the patients are sick. But transferring this into an impact in terms of survival, I think it's a totally different level.
Perry, I have to say, when I heard some of the lectures at the symposium, I better understood why cancer is such a big problem when we understand that cancer cells are very smart because they're cells, and cells are very smart. So cancer cells are doing whatever they can to survive, just like regular cells are doing everything they can to survive. So it's a battle of wits. And Azra's comment that if the cancer is advanced, we haven't made a lot of progress over many, many decades. It's quite disconcerting, but that's, I guess, the reality, and we can talk about the psychological aspects of it, but it looks like medically, there's a long way to go there for us to be able to control stopping cells doing what they want to do, and that is to survive and to replicate.
Yeah, yeah, good. Hi, Dennis.
Hi, I have I guess, like a layman's question. So your argument, or what you're trying to prove, is that the cells act with volition. They have some kind of will or intellect. Is that necessarily incompatible with the idea that they're more mechanical and more like based on the way a machine would work? Because I'm thinking about if you look at the world in a bigger sense. So like as a human, I make choices, but a lot of what I do is like a machine. It's automated. It's not like I'm volitionally trying to do something. The parts of me just work the same way like a car would. So I'm not sure why they have to be mutually exclusive. Again, I'm not a scientist, but why can't you have a sense in which the cell acts for a purpose, but it still has the qualities of a machine?
So I'll take that, and then anyone else who wants to chime in. So Dennis, you're a business owner, so you could appreciate this analogy. If your company is running well and the problems that are popping up are normal problems, everything's in the employee manual, and everybody just follows the procedure, and if they do what they're supposed to, all the problems get solved and all the customers get served. But then what happens when there's an exception, right? What happens if you get a phone call about some problem that nobody's ever heard of before? Or what if an opportunity shows up? Well, a failure to respond to that is what everybody complains about, a bureaucracy, right? And the ability to jazz improvise with that and come up with something on the fly is what we would associate with entrepreneurial creativity. And so I think even in that simple example, you can define a difference between following the rules like an algorithm and doing what you're supposed to do versus doing something new, like completely new. Well, the analogy in cancer is that a normal skin cell or a normal pancreatic cell that's doing what it's supposed to do is following the employee manual, which is what we want it to do. But we have this question of why did Tom Hubyar's pancreatic cells some of them suddenly decide to go rogue and start generating polyploids instead of regular, and proliferating at massive speed, and not doing apoptosis when there's a failure somewhere and a copying error, and so my thesis is that all cells have the ability to go rogue because it's necessary for them for survival in order to evolve. Like, the ability to do the creative stuff is evolution, because evolution isn't random, it's not accidental, it's purposeful. But that ability gets turned against us in cancer. Now, did my answer make sense to you, or did it get to your question? I want to make sure we're in the zone.
Well, I mean, the analogy makes sense. I guess the question is, in what sense can the cell still behave like a machine?
Okay. Yeah. Can I make a comment there?
Yeah.
I think one can get a physical answer to that question by the appreciation that there are two kinds of stability and their topologies are very different. If you're in thermodynamic space, thermodynamic stability, then every system is headed for its thermodynamic sink. You know exactly where it's going to go. But when you're
like throwing a baseball, it's going to land.
That's right. That's right. Every chemical system wants to get to the most stable form for what it is. And that's basically Boltzmann's statistical mechanics of the late 19th century. So you know that if you take hydrogen and oxygen and you put a match to it, you're going to get water every time. That's where it wants to go. Mm-hmm. But with dynamic kinetic stability, the stability of living things, it's not a convergent topology, it's a divergent topology, because the stability of that system doesn't just depend on the system itself, but on its environment. It's the whole thing together. They're not separated. If you have a pool of bacteria of a certain stability in some water, if you add disinfectant to that water, you've changed the environment, and suddenly it's unstable what was before stable. But the point is, once your stability is defined in this broader, more general way, there is no one way that you can prescribe as the way to get to greater dynamic stability. There are many paths, and that means choices have to be taken. And this is sometimes the right choice is taken, sometimes the wrong choice is taken, but the choice is always in the hope of achieving a more persistent state, okay? So that's, so thermodynamics does it, the most persistent state is the most stable state in the thermodynamic sense, but in the world of the living, it's this dynamic, this persistence, which is not thermodynamic, and there's no one way towards this dynamic persistence, and that's what makes life so interesting. And there are so many different solutions to that question, like lions and tigers and bacteria and humans. These are all solutions to how you can survive and be persistent over time, though when we compare the various ways, I'm putting my money on the bacteria long term and not on us humans, for example.
Yeah, so the example of that would be 3 square meals a day. There's all kinds of ways to get 3 square meals a day, but to most people, that's stability, right? So you have these two completely different kinds of stability. So Dennis, I think that cells have a normal operation where they just do their thing, and you could think of that as algorithmic or programmatical or systemic, but then you put it in a new situation and you see what it does. And that's exactly what Barbara McClintock's Nobel Prize paper was about, is what, when I've got this corn plant or I got this culture of cells, when I do something to these things that's never been done in history, what do they do? And the answer was, well, they always do something. So, and I think that's the fundamental question at the bottom of cancer, which we really need to wrap up. We've been going for 2 hours here. Is there anybody that wanted to ask a question that you wanted to get in before we're done? Going once.
I wanted to let everyone know, while people think of questions, that Henry Hang has added his own Q&A session, and that is going to be at 4 p.m. Eastern time on Thursday, the 22nd. I'm going to put that on the chat, but wanted everybody to know that that has just been added.
All right, so yeah, we're gonna have more of these Q&As. They're gonna be with other people. I'm the speaker of this one, and there's it's up here in the chat box. There's Bob Gattenby, Matthias Mann, Dimitar Sasolov, Steve Gollins, Ken Pienta, Jim Shapiro, Michael Levin, and Henry Hang all coming up. So I really appreciate you guys all. This was a fun conversation. Love meeting y'all, and let's keep this going. All right.